Thank you. Morning everyone. My name is Hugo Nicolau. I'm here today to talk about Hybrid-Brailler, which is a solution that combines physical and touchscreen interaction to allow non-visual text entry and editing. So most of this work was done by one of my master students, Daniel. Unfortunately, he couldn't be here today, so you're stuck with me. The other two co-authors are André Rodrigues and Tiago, which are over here at the front, and we all come from University of Lisbon. So as most of you probably already know, since 2008, Apple and later Google included accessibility services in their smartphones to allow blind people to use touchscreen devices. So basically they just drag their fingers over the screen and the screen reader reads aloud the interface element that you're touching. When you hear what you want to select, you just double tap anywhere on the screen. And this is a very effective and simple method and also supports text input. However, due to the lack of tactile feedback, it forces users to just look for the key that they want, which can take time, and then they need to repeat the process for each of the intended keys, again, while receiving auditory feedback. So basically, this is a very slow typing process. To address this issue, over the last decade or so, multiple multi-touch Braille input methods have been proposed. One of the most successful probably was Braille Touch, which was proposed by Frey and colleagues. And in fact, this is a very effective method in improving typing speed, being about 4 times faster as the traditional way of using a QWERTY and the voiceover. However, when you look at error rates, we have some problems because there are some users that can reach up to 50% error rates, which makes this method unusable as a daily keyboard. If you compare that, if you compare physical and virtual Braille keyboards, this difference is even more evident, where error rates can easily double. So what we're proposing in this paper, our original idea was to just leverage the advantages of physical keyboards, such as speed and accuracy, with the expressiveness and flexibility of touchscreen interaction. So this was our starting idea, or the main idea. So we use the back of the device for physical chorded input while freeing the touchscreen for gestural interaction. Obviously, this opens new design opportunities for novel tasks that have been largely unexplored in mobile research, particularly for blind users. So we wanted to go a little bit beyond just text entry and also do text editing. So for the design implementation of our prototype, for those of you who don't know what a Braille character is, you basically have a 3x2 matrix with 6 dots. A combination of those dots makes a character. What you see here on the slide is a Perkins-Brailler, which is a conventional method of writing Braille, where you have 7 main keys, so one for each of the Braille dots and another one for the space key. What is interesting about this method is that each of those dots directly maps or matches one finger, so makes this a chord input method, which is really fast. So we just draw inspiration from the Perkins-Brailler, and this is what was our original idea of just having the physical keyboard on the back of the device. So we wanted to start exploring whether this would be a useful idea for blind users or not. From the start, that was clear that it was a good idea because there are lots of challenges in inputting text on smartphones. So we quickly started exploring button sizes and placements and orientation, whether users would use this on portrait mode, landscape mode, and so forth. And again, from the start, it was clear that there was not a clear preference for orientation. So some people would like to use it on portrait mode, mostly due to convenience. So they just wanted to type a few characters very quickly. Others would prefer landscape mode because it's a more comfortable position to hold the device. And others would like both. Okay? So the trade-off between convenience and for data entry-intensive tasks, they would use it on landscape mode. So we came up with this design. Actually, this was a suggestion by one of our users. So we ended up with a 3x3 grid, where the edge buttons are the Braille keyboard, so to speak, and then the middle column is used for the backspace, blank space, and a function key. So you could use this on landscape mode and on portrait mode as well. So the function key that we have is explicitly edit mode that you press when you need to start editing your text. We could have implemented our system without this key. However, we noticed when people are typing with a physical keyboard, they usually make unintentional touches on the screen just because of the way they hold the smartphone. So we decided to have this key to explicitly engage users in the edit mode and just to build confidence while typing, so they are not interrupted while typing with a physical keyboard. So the operations you could do for additions are cursor movement, text selection, and clipboard operations such as copy, paste, and cut. All these operations start with character granularity, but you can easily change it. So if you press edit button and then one of the three buttons, 1, 2, or 3, 1 for character, 2 for word, and 3 for paragraph, you can change between the granularity of the text. So for cursor movements, users can move the cursor in either direction, left or right, just by sliding their thumbs in the corresponding direction. We specifically avoided complex gestures or symbols because previous research done by Sean Kane has shown that non-visual performance with this kind of gestures just decreases. Also, the only thing we need to be careful with the gesture recognizers were timing issues, because blind users do slower gestures, so our gesture recognizers need to be a bit more flexible and given in terms of timing requirements. For text selection, we leveraged a bimanual interaction technique. So you just hold one thumb on the touchscreen and do cursor movements with the other thumb. To reset the selection, you just leave the thumb if you want to cancel it. If you want to do a clipboard operation, you hold your thumb and you do upwards and downwards gestures to scroll through the clipboard operations, copy, cut, and paste. Regarding hardware that we used, so we built a custom-made PCB with just off-the-shelf components. So we have an Arduino microcontroller that is powered by a USB cable, and we have a Bluetooth module as well. Again, we didn't need the Bluetooth module, but some of Android devices are a bit flimsy in the serial communication using the USB, so we just added Bluetooth to make sure that it would work. And then we have 9 off-the-shelf buttons. All of that is placed inside a 3D printed case. Yeah, and that's it. So after this, we had our prototype, and we conducted 2 user studies. One to evaluate just text entry, another one to evaluate text editing. For the purpose of this presentation, unfortunately, I don't have time to go through both. I'll focus on the second one, and I'll just give you the highlights of the first study. Okay. So in the first study, we did a within subjects study. We compared the Hybrid-Brailler against the software-based approach. And basically, the major results was that they are similar in terms of entry rates, in terms of speeds. However, when you look at accuracy, Hybrid-Brailler is much more accurate, and people, even when they do errors, they identify those errors quickly and correct them quickly as well. Regarding preference, we had split results, so half the participants preferred Hybrid-Brailler, another half preferred Open-Brailler, which was our software solution. Highlighting the need for a lighter case, a more slimmer case, and probably more aesthetically pleasing case as well. So that will be certainly something we'll be working on in the next version of the prototype. Although all participants agreed that Hybrid-Brailler was easier to input text. So, second study, text editing. We recruited 11 blind participants. None of them were able to perform edit operations with their current smartphones. At most, they would just use the backspace to correct text. We did a within subjects study. We compared Hybrid-Brailler against the conventional way of inputting text and editing text on Android smartphones, QWERTY keyboard with TalkBack. And we asked users to do a set of tasks that ranged from delete a character in a sentence, or move a word in a sentence, or correct errors in a full paragraph. So the sentence with errors would be read aloud at the start of the trial, then we would ask them to perform the task, and they would do it. So these tasks were inspired by the work of SIGCHI and colleagues in 2013. In the paper, we also do an analysis of aggregated results for all the tasks. Again, for this presentation, I'm just going to focus on these types of tasks. So basically, we grouped a set of tasks by the most common type of operation. So we ended up with caret movement dominated tasks, keyboard dominated, and clipboard dominated. So we can have a sense of what's going on in these types of operations. For metrics, the first two are commonly used in evaluation studies for text editing. So success rate, percentage of users that finish the task with 100% accuracy, the time that's taken to perform that. And in the paper, we proposed a new metric, which is the editing ratio, that basically gives you how far participants are from finishing the editing tasks, considering that the initial sentence had errors. Okay? So look at the paper for how to calculate that. Okay, let's go to the results. So for caret-dominated tasks, Hybrid-Brailler got 85% success rate against 55% for talkback. This was a statistically significant difference regarding success rate, but when we look at times, we didn't find any significant differences, mostly because with talkback, users could use the volume keys to do cursor movements. So they would use that frequently, and we didn't get significant differences between the times. For keyboard-dominated tasks, so what I'm showing here is edit ratio. So 0 means that the user doesn't need to do any further edit operations. 100% means that the sentence is in its original form, so with errors. So Hybrid-Brailler got about 20%. Talkback got three times worse with 60%. Results here are mostly related with the text entry operation in itself, suggesting that Hybrid-Brailler is much more accurate when entering text. Okay, so last one, selection and clipboard tasks. This was where we found the most significant differences between the two methods. This was the task that participants felt more difficulties overall. So what I'm showing here is just the time, average time between the two conditions, but we found significant differences for all the three metrics, success rate and edit ratio. I'm just showing time to give you an idea of how much long it took for participants to perform edit or selection and clipboard operations. So with the talkback condition, you need to do L gestures to start an edit. For those who could do the L gestures, which is not all, then you need to navigate through multiple menus just to start cursor movement, and then start selection, then end selection, and then multiple menus again to select the clipboard operation that you want, and then you need to do another clipboard operation if you're doing cut and paste. So this took way too long, and it was very complex and demanding. So while Hybrid-Brailler got about 2 minutes to do this kind of tasks, for talkback was more than 3.5 minutes. And this was shown by preference as well. So 10 out of 11 participants preferred using our method rather than the conventional method. So summarizing everything. Regarding text entry speed, Hybrid-Brailler is very similar to a software-based solution. On the other hand, regarding accuracy, our solution is much better than a software one. Regarding editing performance, Hybrid-Brailler outperformed the conventional, traditional method of inputting and editing text in all of these operations. The most noticeable difference were on the last one, clipboard operations. So for future research, we want to further explore this approach of combining physical and touchscreen interaction, and as interaction designers, we believe this opens a new design space that goes way beyond text entry, which connects very well with the first talk that we saw today. And we believe this will be increasingly important in this era of personalized computing, do-it-yourself movements, and 3D printing. So we want to explore this a little bit further other than text entry. And that's it. Thank you for your attention.
So, hey Hugo.
Hi, Jens.
Thank you for your talk. I have a question. So you are designing this keyboard for only the 6-dot Braille. Are there thoughts about extending it to the 8-dot Braille? Because this is very feasible for sending text messages or something, but when it comes to writing complex emails or whatever, there comes to a problem.
Yeah, absolutely. You could extend this for the 8-dot Braille. There's no reason why not. The only thing you need to be careful is the size of the buttons and whether you could use that on portrait and landscape mode as well. But yeah, either 8-dot Braille or even grade 2 Braille, you could extend this approach for that. There's no reason why. We didn't do it yet. But yeah, it's a good idea. Thank you. You can ask another one.
Yeah, so maybe a follow-up question. For what do you need the other 2 buttons in the middle? So you always only pointed out that the topmost is starting the editing mode.
Yeah, sorry, maybe I didn't talk about that much. So the other 2 buttons are blank space and backspace. So you have a function key, blank space, and backspace. You could configure that any way you want in the keyboard. Yeah.
So maybe a follow-up question.
Sure.
For the 8-dot Braille, do you want to use the pinky fingers?
They're not used at all, just to hold the device.
Yeah, but are you imagine that you can use or add additional buttons on the side of the
I'm not sure that would be
for
comfortable.
8-dot Braille?
Because you usually use the pinkies to hold the device in place while you type. Okay. So I'm not sure that they would be comfortable using that for the buttons. So if you use 8-dot Braille, that would be a challenge. I don't know how they would deal with that. Yeah.
Thank you.
Cheers.
I'm Prabhu from the National University of Singapore.
Hi.
I'm just curious, by any chance, did you ask the participants to rate the level of comfort while using the device, especially in the portrait mode, because the amount of surface area is quite less. Like in the landscape mode, they still rest on the sides. With respect to the portrait mode, were there any comments?
Right, so we don't have any data about that. In our user studies, we only use landscape mode. So the portrait mode is definitely more uncomfortable, and people would say they would only use in terms of convenience. If they're doing something on the touchscreen and then they would just input a few characters, they would do it quickly. But if it is for a more data entry intensive task, they would use it on landscape mode, for sure, yeah.
All right, thank you.
Thank you.
Hi, this is Franklin from University of Toronto.
Hi.
I'm really curious about the middle 3 keys. Did you investigate whether they like to use their right hands or their left hands to press those keys? Or it's they try to use both?
We did not. We don't have any data on that. It would be interesting. I'm supposing they use the dominant hand to use the middle column of the keyboard, but I don't have any hard data on that.
And one more.
Yeah.
How you decide what size of the phone and what size of the buttons?
Yeah, that's a good question. So that's the main challenge right now in terms of ergonomics. Obviously, the layout of the keyboard and the size of the buttons need to be different depending on the size of the phone and the way you place the buttons on the phone as well. So if you imagine a big phone, probably the middle column would need to be shifted a little bit more towards the dominant hand or so. The way we dealt with this right now is that you used, I think it's 4.8-inch phone, which gives us the opportunity to do a fairly symmetrical keyboard. But yeah, that's a good point. So you need to be careful if you're designing for bigger phones and bigger layouts. Yeah.
Thank you.
Thank you.
So let's thank Hugo once again and
Cheers.
give all the